Hello, everyone, and thank you for everyone that's joining the YouTube Live today. My name is Matt Lemay, and I'm very excited to present to you something that I think is going to be more and more relevant to traditional manufacturing, and that's generative technology with 2.5 axis CNC. Today's presentation is just part one. Next week, my colleague Brad Tallis, who many of you know, will be presenting part two of this series of presentations. My webinar today will be more focused on the generative and the design side of things, whereas Brad will focus a lot more on actually manufacturing that component. So once again, thank you for everyone that's joining us today. For those of you that don't know me, my name is Matt Lemay, and I'm part of the generative adoption team here at Autodesk. So my role is really working with our customers to understand how to use generative, what it's all about, and really ultimately to make you successful with the technology that we really think is going to change the way that manufacturers bring products to market. So to get started, we just like to cover a brief introduction to generative. Many people are still not quite aware of what it is. So to get started, one of the most important things, everyone likes free. So for the entire month, generative design is free. So if you have an entitlement currently to Fusion 360, if you're a trial user, if you have product design and manufacturing collections, you can use everything that we're showing today within generative design completely for free. So this is a tremendous opportunity. Traditionally, when running generative design, we have a cloud consumption model. We use cloud services to run hundreds of generative iterations in the cloud, and that does cost money. So for this month, you can try it, you can work on projects, you can do anything you want with generative for this entire month. So once again, the ways to get access, and we'll talk a little bit about this in the end as well. You can get access to unlimited generative technology today through a Fusion 360 trial. So if you're not currently entitled to Fusion, or if you don't have a trial, you can sign up for a 30-day free trial, and you can run, again, as many generative studies as you want until the end of the year. Second would be if you have a collection entitlement, if you're currently entitled to product design and manufacturing, you can use generative design as part of Fusion. And then, of course, if you're currently a Fusion 360 subscriber, you can also use generative for free. Now, if anyone's outside of that, or if anyone's within the education community, please feel free to write a question in the chat, and I'm sure my colleague Aaron would be happy to help with that. So to get started, it's really important to think about why generative is really changing the way that we bring products to market. So we really think that generative design is going to be the next major shift within the CAD market. And when you look at CAD over the last 35 years, and Autodesk has been making CAD for a long time, the first major shift was moving engineers from drafting boards to 2D electronic CAD. With that jump, working electronically, the engineer had a significantly higher value than they did in the past. Sorry there. Should be showing my presentation again. Now we saw that exact same jump with the advent of 3D CAD. So now that we're able to look at our models in the context of their assembly, we could add parametric modeling. Again, the jump from 2D to 3D allowed the engineer to have significantly higher value than what they would have had in the past. And this again followed the same when we looked at the release of finite element analysis. With finite element analysis and simulation, you can validate a product for its structure, for its integrity, even for the manufacturing process before you actually produce that component. So again, with each one of these jumps throughout the CAD industry, the value that the engineer has to not just their company, but also the products they're bringing to market is significantly higher within each one of these jumps. Now we see exactly the same thing happening with the next jump to generative design. Now, what's so unique about generative design compared to all of these other advancements within the industry is that with generative for the first time, we're actually clarifying the problem that we'd like to solve. We're setting our objectives. We're looking at our geometry considerations. We're looking at the structure requirements that we might need, manufacturing options. And for the first time, CAD is actually a co-creator within this process, generating hundreds or thousands of viable options that we can start exploring quickly. And these are options that a team of engineers likely wouldn't have thought of on their own. So when we take a look at what this really means, in working with our customers, we've realized the way that people have traditionally brought products to market is that they'll start with a small handful of concepts, maybe 4 or 5. And they'll start to evaluate those for structure, for manufacturability. And in the end, they're bringing a product to market that, while it may have taken them longer than what they would have liked, it's also a product that's likely very similar to other products that they brought to market because they're not exploring a wider range of concepts early. Now, this idea of exploring a range of options is really the true promise within generative. So, with this new generative process, rather than coming up immediately with our own ideas for what the CAD geometry should be, we're putting our objectives and allowing generative to co-create with us hundreds or thousands of viable options that we can start making trade-offs for. Now, while we may be able to bring a product to market quicker, much more importantly than that, we can start exploring options for a design like the one that you see to the right that a team of engineers would have never thought of completely on their own. So if you've been keeping up with a lot of the media and the images of generative products out there on the market today, you may not exactly see how that ties to what you do yet. So when you look at things like maybe the Volkswagen wheel, the General Motors seat bracket, the NASA JPL lander, all of these look very organic, almost alien looking in a sense. So what does generative design mean to those in traditional manufacturing, and why is this so important? So what's changing is that generative design for the first time can now tie the advantages that we get with higher performance to traditional manufacturing techniques as well. So as we look at this motorcycle triple clamp, and this is the project that we'll be looking at within Fusion today, one of these was completely created using generative design. One of these was completely modeled using a human design process. And then one was a combination of both human and generative design. So as we take a look at these three, I'd like to launch this quick poll question here on the screen. So which one of these three icons is a combination of generative design and human design? So you should see a link to the poll has been attached by my colleague in the chat window. And take a look at these three outcomes and think about how you might create a product like this and how generative could actually affect the outcome itself. So we'll leave this open for about 15 or 20 more seconds. It looks like we're getting a really good amount of responses, so I do appreciate that. Okay, and closing down now. So once again, thank you for everyone that answered that question. So within that solution set there, option A, which it looked like a lot of people got, so certainly a great job on that, is a combination of human and generative design. Option B is an example of a purely generative design, and option C was purely human. But what you'll see is that generative design, with its ability to create things that are manufacturable, can actually create us options that are so close to what a human might have created that it's almost hard to tell the difference. So you can see with option B, that is a generative output. It's easily to so it's very easy to machine, it's very easy to manufacture, and it's also higher performing than what we could have created. But what it's also allowing us to do is generative is giving us a solid editable CAD geometry that we can continue to adjust to make it our own. And that's what we see with option A. So once again, thank you for everyone that answered that poll question today. So as we look at it, again, I go back to that question, why is generative design so impactful for traditional manufacturing? And the reason is that for the first time, generative is not exclusive to just additive manufacturing. So when we take an example like this project here, as we're running through generative, of course, we can always set up those organic, the unrestricted, and the additive manufacturing outputs. But probably more important than that, now we can start applying things like subtractive, casting, and even two-axis cutting. So if you were to water jet a cutout, if you were to water jet a plate, you could certainly produce those at the same time within generative. So what this allows you to do within the same study, you can generate the ultra high performing additive manufacturing parts. You can also generate the very prismatic, easy to manufacture parts at the same time. So no matter where you fit, whether it's traditional or advanced manufacturing, generative design has some value that it can attach to what you do today. So let's get to the good stuff and let's jump into Fusion 360. So for those that have seen generative design in the past, or for those of you that don't, we're going to walk through a use case where we'll take that motorcycle triple clamp that we showed in that poll, and we'll start off with that original CAD file, and we'll do the entire workflow of generating for all of those different manufacturing options, exploring, making those trade-offs, and we'll take a look at not just the additive and the unrestricted outcome, but more importantly, we'll take a look at that 2.5 axis easy to manufacture outcome. So the project that we'll be looking at today is a motorcycle triple clamp. A motorcycle triple clamp is the component that connects the fork of the motorcycle with the frame itself. And you can see it highlighted here on the screen. So within generative design today, most people are familiar with working in the design workspace where I currently am. To get started on a generative project, the only thing that we need to do is go to that generative workspace. So if I click on that drop down, of course, many people are familiar with the modeling workspace. You might be familiar with manufacturing and simulation, but you might not be familiar with this new generative workspace within Fusion that allows you to do some pretty amazing things that we'll show today. So to get started, we'd really just isolate to the subassembly or the components that we care about to start generating. So here we've opened up just the subassembly for, again, the triple clamp, the motorcycle forks, and any other assembly components within this geometry space that we might need to consider. So you'll notice that I am in the design workspace. And to get started, I'm just going to click on the drop down and I will go to generative. Now what you'll see happen is I'll lose all of my appearances, the user interface on the top will change. And what this workspace allows you to do is, starting from left to right, go through and set up a generative solve, explore all of the results, and send out a higher performing generative output. Now at the end, I'll talk a little bit about some resources that you can use to try to get started, but something I'd highly recommend for those first time users is if you look to the left of the user interface within generative, you'll see a learning panel. And the learning panel will actually walk you through the entire process in live update to show you where you might be missing things. So again, if you're brand new to generative design, there's lots of resources out there that we'll attach at the end, but I'd highly recommend using that learning panel. So the first thing that we always do within generative design is we need to think of our geometry inputs. So generative design works on three main types of geometry. The first would be a preserved geometry. Preserve is essentially the geometry that we need to keep in within our generative solve. It's geometry that we know that we need at the end. So it could be connections within our assembly, a location where we might attach a bolt to later on. It's anything within our geometry that we know that we need. Second would be our obstacle geometry. So this is the opposite of a preserve. An obstacle is essentially telling generative, generate anything you need outside of this geometry. Obstacles are essentially keep outs. So these could be assembly clearances, they could be moving parts, they could be other components entirely. It's anything that we're telling generative to avoid within our geometry space. And then finally, a starting shape. So a starting shape gives generative design an initial solving point. It's saying iteration 1 can start from here. So a starting shape is typically your existing geometry for a component, but it's also very important to know that you don't have to use a starting shape. So we'll show a workflow in this case where we can use a starting shape and where we might not use one to kind of show some of those trade-offs. So to get started, the first thing that I'll do is we need to start creating or extracting those geometry types for the preserves and the obstacles. Now we'll do that within the generative workspace for a few reasons. That allows us to update all of this CAD geometry and extract features and remove other certain features that we might not want without actually updating that production CAD file. So this is again all happening just within that generative workspace. So the first thing I'll do is I'll go to that Edit Model tab at the top, and this will bring me into a modeling environment specific to generative design. Now you'll see the user interface has changed, and there's a few new tools that we'll cover today. But these are tools specifically created to help you create those preserves and obstacle geometries that we talked about. So as we look at this triple clamp, there's really only a couple things that we need to extract. We know that we need to avoid regions in the fork. We need to avoid other assembly components themselves. And we also need a consistent wall thickness around each one of those fork locations now so we can attach this later on. So to get started, the first thing that I might do is create a sketch on this top surface. I might project the inside circles of all of those preserved locations that we want. And then I could create an offset. So in this case, I could say we want to have a consistent wall thickness of 5 millimeters around each one of those forks. Around this center pin location, we might not need quite as much. So for this, I could say provide a constant wall thickness of 2 millimeters. So now that we have our 3 sketches created, I can press the E key for extrude and just select each one of those profiles and extrude them to the bottom of that component. Now you can see it will automatically default to a cutting operation. And for generative design, we need solid CAD geometry to select for those preserves. So rather than a cut, we're actually going to do a new body. So the new body will allow us to, again, not cut, not create an intersect, but actually create new CAD geometry from that extrusion that's separate from the existing bodies that we have. And this is exactly what we want. So as we press OK, you'll see within my model components folder to the left and within the bodies folder, I've now added these 3 new solids that I'm going to select as my preserved geometries later on. Now, we're all set on our preserves, and that's really all that we need. For preserves, you can think about it as they're pretty much the least amount of information for what we need to solve from. For our obstacles, we're also in a really great place to use the existing components that we have within our assembly, right? So we know that we need to avoid this existing fork location. So we don't actually have to even create new geometry for this fork. We can actually use the existing CAD geometry that's already there. So for this project, creating those preserved geometries is the only thing that we would need to do to get started. So at this point, we can press the Finish Edit Model command, and this will bring us right back into that generative user interface, but now with those 3 new bodies that we created. So at this point, we need to start selecting these to actually specify what they are. So the first thing I'll do is I'll select the obstacle geometry selector at the top. I'll choose each one of those assembly features that we know that we need to avoid right now, and I'll press OK. And as it does that, it will turn them all to red, signifying to generative design, these are geometry locations that we need to avoid. And you'll see to the left, I will also have a tree that will appear saying that I have 3 solids for my obstacle geometry. Now I'll need to do the same thing for my preserves as well. So within my preserves, I can select the preserve geometry selector at the top, select each one of those solids we created. If they're overlapping, I can hold down the left mouse button to select the one that I'd like. And as I do that, you can see all three of those will actually turn to green. So this is all that I need for my geometry space to get started. Again, generative allows us to think of things in the simplest context, looking at the geometry considerations of only what it is that we need and what we need to avoid, and then generative will actually do the rest for us. So the next thing, working from left to right, is we have to set up our loading conditions. So when setting up a generative design solve, generative is going to create the best component for the structural integrity and the system that we're actually placing on this component. So if we need a part that can hold 5,000 pounds or 500 psi, generative will use that information to create the best component for that application. So for this, we're going to start applying load cases. Now we'll actually apply multiple load cases to account for multiple different situations. So in one case, the motorcycle triple clamp could be under tension, and another one, this could be under compression. But generative design allows us to account for all of those different situations at the same time. So for my first load case, what I'm going to do is hide my obstacle geometries to only show the preserves. Now the reason I'm doing that is because loading conditions can only be applied to the preserved geometries themselves. So locations that we know that we have existing CAD geometry. Then next, I'm going to apply a constraint in the middle of this assembly, and then I'll apply a force on each side. So here we can set this 1,000 pounds in the positive Y orientation, and I can clone my load case to then do the opposite. So cloning the load case will keep everything the same, and in this one we'll do negative 1,000 pounds in that orientation. Now, just as a note, if this is going a little bit too fast, again, we do have a lot of training content, not just for this project itself, but also for generative that we'll share at the end. What's really nice about this project for the motorcycle triple clamp that I'm showing is this is CAD files that you have access to right now. So within your project panel to the top left, if you go to generative samples, you open ready to generate, you'll see the generate motorcycle triple clamp, and you can actually follow along with this recording and the training content on everything that we're showing today. So we have the ready to generate file as well as the ready to explore, which has this set up so you can just view the results. So to get back to it, we've set up multiple load cases. We have our geometry set up. We're nearly there to kicking this off in the cloud. The next thing that we need to do is set our objectives. So again, working from left to right, objectives are essentially what we're trying to accomplish within a generative solve. Now this could be we'd like to minimize mass as much as possible, but with a limit of reaching a factor of safety. We could also specify a specific mass target that we'd like this part to achieve, again, while keeping that factor of safety limit that we've set. So in this case, we can say let's minimize mass while keeping a factor of safety of 2, and then pressing OK will lock that in. Next, we'll set our manufacturing techniques. Now, this is the most exciting thing for everyone that uses generative design out there, because this is actually what makes these generative design components real. This is what actually makes them manufacturable. So the first setting you'll see within this manufacturing tool at the top is production volume. Now, this is very important because what we've recently done within generative design is we've partnered with a company called A Priori Technologies to look at all of these generative design outcomes that we're creating and compare not just the performance improvements of each one, but also the estimated cost for each process, right? So you can imagine if you had an additive component versus subtractive component, you can now put a price tag to each one of those to make the correct trade-off. So in this one, we can set our production volume. We'd say we'd like to make 1,000 of these parts. The first manufacturing option that we'll select would be unrestricted. This is what people are most familiar with when they're looking at generative design. This is saying just create the perfect component, ignoring any specific manufacturing constraint. Next would be additive manufacturing. So again, within this project, we can set up an additive manufacturing constraint. This will allow us to specify an overhang angle and a minimum thickness and provide us 3 self-supporting additive outcomes. And then next, the most important for what we're doing today would be milling. So milling constraints allow us to take real-world CNC applications to generative design components, which this is brand new. So of course we can do a configuration for, let's say, 3-axis CNC. In this case, we can look at things in the plus and minus Y orientation. So you're thinking about how this tool will actually mill this component. We can also look at a 2.5-axis operation, and I'll talk a little bit in a minute about how those vary from 2.5 to 3-axis. Again, we're going to be looking at the Y orientation for the cutting direction. And we can also specify a 5-axis orientation to make something extremely lightweight. So we can also go through and select 2-axis cutting. Again, we're going to look at the Y orientation for cutting, and then we can do casting as well. So after we've selected our manufacturing options, what's really important about generative design is if you set one manufacturing option, it will eventually cost you the same as if you set all of them. So it's always the best application to look at all of those different manufacturing types and make trade-offs. Next, we'd like to look at our materials. So very similar to those manufacturing types, the more that we put here, the better. Again, we're trying to make trade-offs for all of these different outcomes. So currently we have an aluminum alloy within the study, but we'd also like to add other materials as well. So we could go through and say, I'd like to add steel just by clicking and dragging that to the top. I'd like to add maybe a titanium. Whatever material you would like to solve, you can add this to the top of this window, and this will give you a unique result for each one of those material and manufacturing options. So after I've selected a number of materials, at this point we're pretty much ready to go. The only thing that we would have to do is run our local preview. So again, generative uses cloud solving to run all of those generative iterations that we talked about, but before pushing it to the cloud, we can run a local preview to make sure that everything is going to generate the way that we might expect. So you can see this transparent, very coarse approximation of what generative is going to do. And really what we're looking for is just that all of our preserves are connecting in the way that we might expect, and that the geometry is either adding or subtracting. So at this point, we've seen everything that we need to continue, and we'd be ready to solve for generative design. Now, I want to cover a couple different things as well. So we talked about this ability to look at different manufacturing options. And this even comes into place when we're looking at 2.5 versus 3-axis subtractive manufacturing. So within generative design, again, we set up that unrestricted, the additive, casting, all these CNC options. But to really understand the importance of each one, you can look at it even just looking at the CNC options. So within generative design for this project, we set up a 3-axis milling operation and a 2.5-axis milling operation. But the major advantage of looking at all of these is that the result that you get from generative is going to be very unique for each one. So the 3-axis operation has a little more freedom to generate things that are a little bit more organic. So you see it can get a little bit smoother on the edges. It can just create a little bit more complex geometry. Whereas 2.5-axis generative design is actually creating geometry with a series of pockets. And what that allows you to do is truly look at the trade-offs between that slightly higher performing 3-axis milling part and that slightly less performing 2.5. But now we can also look at the manufacturing time itself and then the manufacturing cost. So you can see that 3-axis milling part is actually still milling that component, while the 2.5-axis, because of those pockets, is actually already completed. So again, this is where generative design really brings the power of everything that we talk about with creating higher performing products and the design for manufacturing process to traditional manufacturing techniques. So to get back into Fusion, we are ready to kick off this solve. So the last thing that we would do is we would go over to the Generate tab here. And again, most exciting thing, for the rest of the year, all of this is free. So it doesn't matter how many cloud credits you have, as long as you have a trial or a commercial or a collections entitlement, you can go ahead and run as many as you'd like. So I would press generate one solve, and this would all launch to the cloud. So I'll quickly skip ahead to the results of this so we can see the value behind generative design. So after you've run that generative design solve and you've waited 30 minutes, 45 minutes, whatever it might be, that entire time it's running in the cloud. So it's not using any of your local processing power. You can shut down your laptop, you can grab a coffee, whatever it is that you need to do, generative design is going to continue running. So after we've kicked off the solve, we can go to that explore environment and we can start reviewing all of these results created for us from generative design. So as we scroll through, it can be pretty overwhelming at first when we look at all these thumbnails. We can see a range of different options. Many of these look very unique. We have all these different filters on the left, and I'll quickly talk through how we can start selecting on the ones that are most important to us. So the first thing that you'll see as the generative outputs to the top left is you'll see what's called converged and also what's called completed. So from this one generative design study, we have 51 converged solutions and we have 15 completed solutions. Converged means the geometry is finished solving and it's actually met that solving criteria that we set. So it could have been a factor of safety or it could have been a mass target. Completed means that generative has completed its solve. There's no more geometry manipulation that generative can do. However, it has not met that objective requirement. And this is actually really impactful for us. So if we set a material, like if we had set a plastic material in this situation that wouldn't be strong enough, generative will try and try and try across all of its iterations to reach that solving criteria, but it may fail coming back as completed. So you'll also see all of these thumbnails on the screen. And as we hover over one of the thumbnails, you'll see this timeline slider at the bottom. And as we drag this from left to right, you can see all of the iterations that generative actually went through to produce that final component. Now again, to go back to the screen to the left, you'll see our manufacturing methods have also a range of filters on them. So as we isolate our unrestricted, we can start taking a look at how manufacturing settings actually influence each one of these outcomes. So first, we can click on one of our unrestricted results. So this is one that's created for a titanium material. And again, with unrestricted, it's creating geometry that is basically ignoring manufacturing constraints and just making the perfect part. So many people use unrestricted either as a design guide, as saying this is the ultimate geometry that I could create for what I'm trying to do, or as a method to bring to metal additive manufacturing. Either way is completely useful. So that's our unrestricted, and that's what people are probably most familiar with when they think about generative. Second would be our additive manufacturing results. So within additive manufacturing, you'll see the outputs are going to be a little bit different because additive manufacturing actually does have some real constraints that we applied. We applied a printing orientation, a minimum feature size, and also an overhang angle. So in this case, you'll see that my printing orientation is in the plus Y direction. So meaning this flat surface on the bottom would print normal to our platform, and the rest would all be self-supporting geometry from there. Now, where this gets really exciting, of course, those additive and those unrestricted are very exciting to look at, but for many people, they're still not practical when it comes to high volume manufacturing. So this is where putting traditional manufacturing techniques at the same time adds value. So for this same project, of course, we have, the unrestricted and the additive ones, but we also have two-axis cutting. So if you were to cut this out of a plate with something like water jet, generative design is creating essentially an extruded profile for this application that we can produce very, very affordably. And when I talked at the beginning about the estimated manufacturing cost that generative is actually providing us, this is telling us that this part to machine would only cost on average $51. Now that's probably 1/10 of the cost of those additive parts. So it's not quite as high performing, but generative is truly giving us that entire range of cost versus performance trade-off options. So that's our 2-axis operation. And the thing that we're most focused on today would be our 2.5 axis. So 2.5 axis is creating, again, a generative component that is ready for an easy to machine operation. So in this case, similar to the 2-axis, it's creating that profile on the outside. But with 2.5 axis milling, it's creating a generative component that we can cut out these pockets, create not just a lightweight component, but one that's also very affordable to manufacture. So we just showed that 2-axis operation. That one costs $50. With this one costs $60. So slightly more expensive because there are some new machining operations that we need, but it's also higher performing. So then to quickly go through the rest of these, again, we have our 3-axis milling operations. These ones can create components that again can be machined, but these might take a little bit longer to machine what you're seeing on the screen. Same thing with our 5-axis. Because our 5-axis has a little more freedom with that geometry, we can create things that are pretty organic, again, higher performing, but these are going to cost more to machine as well. And then we have our casting components. So we're also generating components that could be ready for a casting operation. So we won't get too far into casting today, but with this solution, it's trying to make a component that's meeting the minimum and maximum wall thickness and also the ejection direction that we set at the beginning. So as we look at all these outcomes, again, it can be a little overwhelming to try to find the right one. The ones that engineers I work with like the most would be the scatter plot view. Here we can take all of these different outcomes represented by points on this graph, and we can start filtering down to the outcomes that we're most interested in. So we can say, maybe I'd like to view stress on one side and maybe mass on the other side. And again, each one of these points represents a different material and manufacturing option. From here, we can select and filter down and really make the trade-offs that we talked about before. What's also really exciting is we talked about cost. We can do this same analysis with cost as well. So now we have our cost analysis on the y-axis and we have mass on the x-axis. So now we can actually think about, well, how much would each one of these parts cost to manufacture? Is the high performance part worth it, or is cost more important? Either way, we have that entire range of options. So let's filter this down to something that's both lightweight and also easy to manufacture. And that actually falls into that 2.5 axis operation that we found before. So as we go to that outcome view, if this is the part that we found, it's lightweight, it's cheap to manufacture, this is the one that we'd actually like to produce. So when we're looking at one of our generative outcomes, you'll also see an iteration slider at the bottom. And this is actually walking us through the entire range of steps that generative design went through to create that final outcome component, starting from that initial geometry connecting all the preserves, to then either adding or subtracting material to get to that final outcome that's minimizing mass. So here you can see it started creating pockets, it's continued to expand those pockets, change the outside profile, to the point where in the end, we get a very easy to machine output that to most people, this wouldn't look generative yet, but as we look towards the future, generative will be applied more and more to traditional manufacturing. Okay, so we have all of these results. That's great that we can see it within this CAD window, but what do we do next? So what's great about generative design, because it is at the front end of that product cycle, is that generative allows us to take one of those outputs and actually create solid editable CAD geometry from it. So within any one of the iteration views, we can just go to the Export tab at the top and create a new CAD file from that outcome. So first, I'd like to show an unrestricted outcome. So as we looked at all of those generative outcomes, maybe performance is the most important thing and it outweighs cost, and we can export one of these unrestricted generative geometries. So here with this one, we have that very organic geometry. All of that was created for us through that generative process. And all of this is also very open for us to edit. So it's not a mesh that we would just have to remodel over. This is geometry that we can continue to adjust. So you'll see a timeline at the bottom. And just to quickly walk through that as we scale it to the left, the first thing that it's doing is it's bringing in those preserved geometries we created in the beginning. So think about it. This is the only CAD geometry that I had to create within this entire process, are these three essentially primitives. Next, it brings in those obstacle geometries that we selected from our assembly. So those forks and that assembly pin. Again, something that I didn't have to create. Then what generative did is it created this very organic generative geometry, connecting those preserved geometries together for us. And now that it's within a T-spline model, we have freedom to adjust this as much as we need. So if we looked at this model, we might see these struts here, and maybe we'd actually like that thickened. So if we just select one of those faces, go to edit form, change the coordinate space, and feature selection, we can automatically select one of these struts and we can thicken it. Whenever we're done making these changes, we can finish our form, move that slider to the end, and it will recombine as that one solid editable geometry that we can work with. Now at this point, if we've made changes to this output generative geometry, how do we know that it's still compliant to those load cases that we set at the beginning? So something that's, again, pretty new to generative design, and if you haven't used a simulation workspace within Fusion, I'd highly recommend it. But all of those load cases that you remember that we set up at the beginning here within the simulation workspace, all of these are brought through from that generative design solve. So we don't have to reapply the material, reapply the load cases. All of that will come through for us, and then we could validate any changes that we made to that editable CAD geometry on the back end. So this will take just a few seconds as it's bringing in all of those loading conditions, the material types, and it will bring that into the simulation workspace. So here you can see we have our load cases, tension, compression, we have our material, so we don't have to reset this up every time that we make a change to that generative output. Now, the point of the presentation today was to not look at generative in the context of a model like the one you see on the screen, very organic, unrestricted, and probably only able to be made through additive. The point of this presentation today is to take a look at a generative outcome that's not just higher performing, but also easy to manufacture. So with this one, we would also output a 2.5 axis generative component. So again, the component you're looking at on the screen to many people does not look like a generative part, but it was. It was truly created within generative. And at the same time, when we output that unrestricted and very organic model, we had that timeline at the bottom. And here we get something very similar. So as we scale this timeline to the left, you'll see the same formula. You'll see that original preserved geometry, those three solid bodies that we brought in. Next, you'll see our obstacles, again, those forks themselves within the motorcycle, assembly components. And then what generative design is going to do is it's going to make a series of sketches and extrusions for that 2.5 axis geometry. So to quickly show what that's doing, within generative design when we're looking at 2.5 axis operations, generative design is creating a series of layers and pockets that can be easily machined through a single setup direction. So on one outcome type, we'll have 3 layers within our geometry. On another one, we'll flip that and we'll actually machine from the opposite direction. And then there's a third outcome type that will actually have 5 layers and then providing us 2 setup orientations. So in this case, it would be the plus and minus Z. So outcome number 3 is actually what we're looking at here. So this actually has those 5 layers. And as we scale this to the right, you can see that it's created those pockets for us. And if we needed to change anything, it's just as easy as going back into the sketch within that timeline, moving control points within our pocket, maybe even taking some of these out to smooth out the geometry, finishing the sketch and moving that forward, and then that will automatically re-update that generative model itself. So again, we looked at 2 generative outputs. One is probably the one that I think people are more familiar with. It's very organic, alien looking. It's great for those people using additive, but not so great for everyone else. But what's really, really exciting is that generative can now do traditional manufacturing outputs as well. something that's easy to machine. And in part 2 of this presentation next week, my colleague Brad Tallis will bring this generative component into the manufacturer workspace within Fusion, and he'll actually look at strategies for machining a component like this. So at this point, I think we covered a lot today. I'd like to thank everyone that joined the presentation, and we have about 15 more minutes. I'd like to answer as many questions as we can that are coming in through the chat window, and I'd also really like to talk a little bit about some of the resources that are out there for you to use generative design as well. So please feel free to type in questions into the chat window, and I'll try to answer those live. We have a question or a comment that says, "We love Brad," and I agree. I also love Brad as well. So I'm going to quickly talk a little bit about some of the resources that are out there for learning generative design. For those that are not familiar with the Fusion 360 adoption portal, there's training content for not just what we talked about today within generative design, but everything from moving from a different CAD CAM system to machining to T-spline. So that's a really great resource that's out there if you saw something about generative today that you'd like to learn more of. We have a question, well, maybe a comment here. Great stuff, Matt, but I have no idea how generative can help me. It looks amazing. So I think that's something that we need to do a little bit more to address, right? And I think it really comes down to when people see generative design outcomes, it's creating something that for many people is unattainable. It's those organic, additive components conventionally. But our goal with generative moving forward is to make something that's traditionally manufacturable. So it could be in this case 2.5-axis CNC, or it could be in the future making something that could be a welded frame structure. Either way, it's something that can relate to traditional manufacturing. There's another question here. This one from Michael. Is there an option to run simulations locally? So you can run the finite element analysis simulation locally. Generative design, however, because it runs all of those iterations, all of those manufacturing types, that does have to be run in the cloud. But again, the good thing, all of that is free for the rest of the month. So again, please feel free to type in any other comments, questions there on the chat. Wait on the line here for another 10 minutes. Okay, I think that pretty much covers all of the questions that I saw. Once again, thank you for everyone that joined the webinar today. My colleague Brad will be online next week to show the second half of this, where we're actually bringing that part to the manufacturing environment. And once again, thank you for everyone that joined, and hope to work with many of you in the future. Thank you.